In this video, we are going to talk about if we can design, for example, a motherboard at home. We are going to talk about complex design. Is this what we are going to talk about, Istvan?
Yes, but we will be focusing on the work environment instead of the electronics itself.
Okay. So, and this is very important topic because I think I met many people who ask me questions like, I have no experience in electronics. Can I design a phone? Or I have no experience in designing boards, or I design an Arduino. Can I design motherboard? So I think it's very important to mention what are the differences between like hobbyist and professional design, and also all the kind of different levels of design. And I think this is what we can see also on this very first picture. Can we talk a little bit about this?
Yes, so I got some pictures of different complexity boards, and these arrows on the top just indicate how a learning process works.
Not like the
So
purple one.
no. So someone might think that, okay, I'm going to design a computer motherboard and just start with that. But actually, it's several years until you get to the point where you design your computer motherboard. You have to design smaller designs first, a little more complex designs, a little more complex design. Computer
And
motherboard is actually very complex.
why? I
And
think many people would ask like, why? Why we can't jump from the small one to big one? What do you think?
so the bigger designs have several subsystems. While in a simple design, it's just one. And in a simple design, there's just a microcontroller and it's easy to understand it. But in a bigger design, you have to work out the block diagrams for these different subsystems. You have to perform a lot of analysis. Some of it is simulation. Some of them are basically data analysis from data sheets and from other places. And you spend a lot of time on those and then you start designing a schematic. But even the schematic would have like 100, 200 pages for a computer motherboard. And
Hmm.
in order to navigate my own 200-page design, I have to have a lot of preparation work done beforehand.
Hmm. I think one of the examples what I very often use to explain why we can't simply just jump from nothing to designing motherboards is I remember when I was starting with hardware design and I designed, let's say, I don't know, a circuit with maybe 10 wires, and I made mistake in 5 connections. Yeah. And I spent, I don't know, 1 or 2 hours debugging this very simple circuit which didn't work. And we can't really make, I don't know, if our board has thousands of connections, we can really make mistake in thousands of connections. Yeah, correct?
Yes, we have to develop our designer skills. So the percentage of errors in a design will go down, further down. So when you have a board with 10 components, you can have 5 mistakes on it and you will still fix it in a few weeks. If you have 1,000 components and 50% of that are, it will be bugs on top of bugs on top of bugs. It would not be possible to resolve it. So you have to have a good low error skill set by the time you get to your first complex design.
Yeah, and I believe I've seen it many times. Almost every person who is starting with hardware design, they make very similar mistakes like pin swapping or footprint swapping, or everyone make this kind of mistakes. Or did you when you were starting? When I was starting, I made this kind of mistakes. RX-TX connection swap, and
Yes, some of the analysis is that we make sure that RxDX are not swapped and you use spreadsheets and text documents to ensure that. Um, the typical mistakes come from misunderstanding the data sheet of the components, I think. And it's also a skill to, when you open a data sheet, now you know what to look for, but this only happens after several designs.
hmm. Exactly. Okay, so let's go through these slides what you prepared, and let's have a look what you have inside.
Okay, so this again, this is just to clarify what we are talking about. We will not be talking about specific circuits or processors, anything like that, because in engineering, there's a lot of additional work that we do around the projects. And also we have to understand what we have to do in a job. Most of the designs are not done at home, but in a job at a company, and there are lots of tasks in every project, and the audience has to understand that what those tasks are, where to learn them from, who to ask about what the tasks are, or how to do them.
Okay, so again, something from my own experience. I remember when I was starting with hardware design, for me, designing board was to design schematic correctly. That was designing the boards. But that's not it's not so simple, correct?
Yes,
Designing correct schematic, that's not designing board. It's only very small
there's
part of the design.
yes, there's so the we will talk about how the schematic layout design splits as we get to more complex designs. People starting with very complex, very simple designs, especially as a hobby, they will do the schematic layout together at home, or even at small companies, they will do that. But as you get to more complex, there are different person will do the layout design. But still, the person who designs the schematic has to understand what goes in the layout and start a lot of preparation work for that layout. For example, negotiating the stack up, calculating layout constraints and other things.
And I mean also like production itself has to be
Yeah,
considered
yes,
sometimes. Component
yeah,
selection and this kind of testing.
procurement, the components. If I just buy an IC right now, that's not useful for a product because it has to be available at a certain price, a certain lead time for the product lifetime. If you design a circuit for a company, they are doing it to make a product they want to sell for a certain number of years, and they have to be able to sell it for a certain number of years. So that's part of the design. They design it in a way that it will not run out of available components after a first one or two production runs. And I also want to point out that hardware engineering is a very hard profession. So most people with electrical engineering will end up doing something else, like test engineering, programming, procurement, manufacturing. So it's a little bit like sort of sports, where you cannot just join a sports team and expect a gold medal in the first tournament, right? And so some people might find that they get into hardware design and they find it too difficult, and then probably they drop out. But those who can make it, they can progress further and further in their career. I showed the diagram about the complexity increase of the designs. So someone might drop out after the first design or the second, or maybe just stay at a certain level, which is fine because there are many products that are at low complexity. For example, when you buy something for your home on Amazon, some electronics, those are not very complex. People have to design those as well. But some people want to get into complex designs, and they have to have the ability and the perseverance because they have to study a lot, read books, read articles, conference papers. In the first simple designs, you don't have to read much. Maybe read a simple book or one book about basics.
I
But
think you
if
have
you,
slide about this.
yes, I think it's
I've
somewhere
seen it
later on.
somewhere.
Should we jump to it now or
Yeah, you
just?
can jump there. You can jump there.
Okay, so this slide just demonstrates if you want to design a microcontroller board, just find one good book on Amazon and watch a few YouTube videos. That for complex designs over the years we have to read a bunch of books, not just one. Read magazine articles, conference papers. If you work at a large company, they might provide trainings in the job about high-speed design, circuits, manufacturing, and other kinds of topics. And many companies, there's something called mentorship. So there's a lot to learn from mentorship, although that's not the only route. Some people can learn by themselves by researching things and reading. Some people can rely more on reading and less on mentorships versus some other people who rely mostly on mentorship and don't read much, maybe one book.
How did you learn?
I didn't find a mentor, so I had to learn everything myself. And this is called autodidactic learning.
Same for me. I had to learn. I mostly learn from designing more and more and more complex boards, and then reading data sheets and design guides and all the recommendations. That's how I learned.
Yes. Okay. So we have some other slides. For example, people fresh graduates or students usually are not exposed to these industrial and data
Mm-hmm.
center and the avionics type hardware, but they exist. Actually, there are a lot of them. For example, when you use your cell phone, you're not just using the cell phone itself, you're using the cell tower. There's a lot of very complex electronics in it that communicates with data centers, with servers and switches and routers, like you see in the bottom. Those are designed by electrical engineers as well. So, but even though we are using a phone, it goes through the data goes through these equipment. We don't see these equipment, we don't touch them. It's not in the same room where we are, but they still exist. They need to be designed. So I think most electrical engineers who design circuits actually end up working on these
Mm-hmm.
because a larger number of designs in the world for these. But
Again, this actually happened to me. So even I was designing motherboards. These were industrial motherboards. So people couldn't really buy like in like a regular shop and use it in their PCs. But these were the motherboards which are inside of these boxes what you are showing in these
yes.
pictures.
Okay, so students are graduating, they have to expect to not most of, I think probably 99% of them will not be designing TVs, laptops, or cell
Yeah.
phones. So that just should be expected, and don't be disappointed because many of these designs are probably a lot more interesting than laptops and cell phones.
Mm-hmm.
Okay,
This is very good point. It's a very good point because I think many people exactly expect they will be designing laptops or something.
yes, and most of the non-consumer, like industrial, aerospace, data center, come in a metal chassis. These are usually quite large, like some of them as big as a refrigerator. Some of them are maybe you can hold it in your hand, but it's quite heavy. So typically either a sheet metal or a aluminum milled out aluminum case, and there are multiple circuit boards in it. And then one or more persons design one circuit board, and then the whole system is designed by a team. There are lots of mechanical parts in these, all the sheet metal pieces, all the guide rails, front panels, fan assemblies, and all kinds of things have to be designed. So there are a large number of mechanical engineers in these teams that we have to work with. And then the board, as an electrical engineer, we typically design a board that gets assembled with some mechanical parts. And they are not in a nice case like in a cell phone, for example, but it's more fit for a purpose, but not for a home use.
Yeah, yeah.
This again about complexity. There are low complexity boards. This example is like a thermostat for a fish tank, or there is a GPS in your car. These have to be designed by electrical engineers, but they are not super complex. To someone who is just graduating, they might think that it's too complex, but actually the complexity goes way up in other types of products that are out of reach for consumers using them at home. There are this board actually in the third one is used by CERN, by physicists in a research institution. You cannot buy this in a shop, obviously. Now, interestingly, now the fourth image is a computer motherboard. You can buy that as a consumer, but still, it's very complex. It's probably the most complex consumer electronics that you can get. And then even more complex systems or boards are using those industrial applications that we talked about. This is again about complexity. Some people might find this complex. So why are there 10 components there? What do they do? But there can be thousands of components. So
That's
it's
exactly
almost like
what I was mentioning at the beginning. I connected like these two transistors and it didn't work.
Mhm. Yeah, I have the same experience. Okay, there's this slide. I don't want to go through all the numbers, so I'll leave it on the screen. The viewers can pause it and just look at it. This explains really how the complexity grows and what other things happen with the more and more complex design. For example, the number of people working on a project will grow exponentially with the complexity. With the basic boards, just one guy can do hardware, software, layout, everything. But for a big industrial board, there might be hundreds of software engineers, several mechanical engineers and test engineers and so on. If you can move on, I guess.
Yeah.
Misconceptions. I think maybe we should go through these,
Yeah,
right?
let's go. I when you sent me this presentation, I went through this and yeah, I recall.
Okay, so when we deal with the first single or simple design, probably we don't need to deal with signal integrity, but it doesn't mean that no one has to deal with signal integrity ever, and signal integrity doesn't exist. It does exist. All the industrial designs are heavily dependent on it. So I heard someone recently saying that he didn't consider signal integrity. It works fine, so he dismissed the whole concept of the discussion.
So what does it
That's a
mean, signal
misconception.
integrity?
Well, simple designs usually have slow signals and just a short trace, while these high-end designs have much faster signals, several gigabits per second, and there are many signals near each other that try to interact with each other through electromagnetic waves. So that's really the signal integrity that they have to deal with.
I would
I
like
think
to point out it doesn't have to be. I remember uh, two very early designs what I did. So first one was a keyboard, which was a panel of a device, and it was simple keyboard, just pressing the switches, but it had problems, random interrupts, and I never at that time when I was, I don't know, like 18 or maybe 20 years old, I was like, I'm going to add a capacitor and it's going to fix it, and this kind of approach. I had no idea what's happening. And then second time I designed a two-layer board with a whole bus on top and bottom, all the tracks were crossing, and it worked completely randomly. Like it was working, one board was working fine, then other batch was not working, or it was working for 1 hour and then it crashed or freeze it. So even like smaller projects, they still can have problems with signal integrity. People just
yes, you're
may
right.
not find out, or they think it's normal. It's normal. My board freezes once a day. It's normal. It's not normal.
Yes, it's related to reliability. And when a company makes a product, they have to make it such that all the 10,000 customers who buy it all have to use it all day without crashing 20 times.
Exactly.
Now, the signal integrity can be so bad that it never turns on, or it can be a little bit bad that every week it crashes and you just lose your work once a week. So somewhere in between.
Yeah, exactly. I think that's very good point. It's a lot about the reliability of the product. Yeah.
Yes. Sometimes when we say the word hardware, some people associate a certain type of software, not the actual circuit board, but like there is a programming for making a website versus programming for a microcontroller, and it's the latter being hardware. But it's not. It's still software. So
That's the
we are
point
not
too.
talking
Yeah.
about, yeah, we are not talking about writing programs for microcontrollers here. And some people think they don't need to read books or papers. It might be true if they stay with the very simple designs, but still they should probably read one book at least. Something like Introduction to Microcontrollers or Basic Electronics, something like that. Some people think the microcontroller board is complex, but it's more complex than
Blinky.
yeah. And we discussed that someone might think that they can start electronics with complex on day one. Like I never designed electronics, but I start today designing a motherboard. That doesn't happen. It has to go step by step with increasing complexity over several years. Many people think that designing is just schematic and
That's
PCB
what I meant. Yeah.
routing, but actually for the very basic designs, it is. The microcontroller board, it is, but for more complex, there is a lot of additional work that has to be done. And then another misconception is that we design electronics is just electronics, but actually there's a lot of software in it. The most complex industrial stuff have several times as many software engineers working on it than the number of hardware engineers. And the hardware has to be designed to work with that software. So it's a hardware software co-design
Mhm.
is also an aspect for complex designs, but for simple designs, it's not really
Again, I
considered.
would like to point out, I remember this because when I started designing my very first operating system running board, uh, I actually learned that it's really good to uh, stay with reference designs because sometimes you can use also different chips, but writing drivers and making these chips to work can be sometimes a lot of time, even more time than designing the board itself. And sometimes it may not be even possible to actually combine some chips together because sometimes there are silicon problems or something like this, and they may not follow up the protocols properly. And then you end up with a board which is not work and with the chips which are not working together. So that's something what I would like to point out. Sometimes or it is very important to actually understand if you can use this specific chip with this specific software, and if you can connect, for example, these chips together, and if it was already proved they will work together.
Yes, this has to be considered at the beginning of the project, a planning phase. For example, you want maybe management or maybe marketing wants 5 features in a product, but for this one of those features, you might have to write a big driver package that would take 6 months. But if you drop that feature, then the whole product can be developed in half time. This has to be calculated and considered carefully.
And I think there are sometimes people underestimate how difficult it is, for example, write drivers, because writing
Mhm.
drivers for Windows or Linux, there are not so many people who can do that.
Yes, so there are also the BIOS. So when we design a
BIOS,
motherboard,
exactly.
ideally, we try to make it such that the eval board BIOS will work on it as is. If not, then just 1 or 2 changes that are really necessary. But you have to have, that's one of the analysis that you have to do as a hardware designer, is to analyze the differences from the eval board and collect all those differences in a spreadsheet and try to assess the amount of work needed for hardware and for software for each of those items, and then with management you can decide whether which of those items have to be eliminated or for example, if you eliminate one item, you might have to work more on the hardware but less on the software. Let's say in some cases you might have to spend an extra 3 days on the hardware design to save 6 months on the software design,
Yeah,
or vice it can be vice versa as well.
yeah, I agree. Okay, next one. What is the next one? Yeah, I will make a computer motherboard at home. So, why? Even if they design it, I think it's going to cost a lot of money.
Yes, and they would need access to data sheets of the processors, which these companies who make the processors, they will not grant access to those data sheets to a person. They will do it to a company, but that company has to prove that they are capable of making such products, maybe with some history of making products in the previous years.
This is very,
That's
very
one
good point.
reason.
Very good point. I think many people they don't understand this. I see it even in forums like I'm designing these motherboards where I can get this data sheet from Intel processor or something like. Mm, you need to have a exactly what you explain, a company which has a proof that they can design this kind of boards, because these big companies they don't want to spend their resources teaching or supporting a companies which are not going to finish the project.
Yes, and they also have to sign an NDA, which is a type of a contract, and they will just not sign an NDA with anyone.
Yes, exactly.
And I mentioned this 1978 here because there was a guy who designed a computer motherboard in his garage. It was very famous, but it was in 1978. That was a different world. Probably the data sheets were available in magazines or something. I don't know how it was before I was born. And but these days it's not possible anymore.
I was already
Yeah.
2 years old. I can tell you.
Okay, that was Steve Wozniak at Apple. Okay. Yes, so many people assume that electronics is simply what they see in their own home or in their own hands, a cell phone and a TV and a laptop. But there is a lot more. We talked about this a few
Mhm.
minutes ago. And again, this YouTube video comes from my cell phone, but actually it comes from cell towers and data centers and the internet infrastructure, which is full of electronics. And a lot of engineers work day in and day out designing those. Another thing is about career expectations. Like, these computer motherboards are very interesting. Oh, let's apply for this job, and then I will design the next computer motherboard. And they will say, "Ah, no, thank you," or they will ask, "What have you done so far?" Well, nothing. Then maybe apply for a job at a small company where you can design your first circuit board with 2 transistors on it, and then the next one with 10 transistors on it, then with a microcontroller, and so on. So it takes years, and even then, these jobs are very scarce. So most people don't qualify for it, even after working in electronics for several years.
You have to be also, you need to have also good people skills, I guess, for this kind of jobs, not only hardware design skills.
Yes, and experience working in a team. So you have to know what to expect from the teammates, what they expect from you, and you all have to negotiate those things. Even though you talk about technical things in your job, you have to be able to negotiate those with other people, because most of the electronics is not done by one guy, but by a team, a large team. It doesn't mean a team of hardware engineers. It means a cross-functional team of various different types of engineers. And then a college degree guarantees a job at a famous company as their main designer. Actually, even for fresh graduates, companies are looking at, well, depending on the company, but some companies look at your grades, which school you went to. Other companies look at what activities you did while you were a student. Did you attend an internship, and what did you do in that internship? Did they give you some interesting tasks? Did you complete those tasks in the internship? Or in my case, I did a lot of hobby electronics while I was a student, so I had design experience from that. In my first job with a small company, they appreciated that experience from the hobby projects.
I think for same reason I've got my very first job, because I already had experience from university designing quite like microcontroller, DSP, and all these kind of boards. When I receive CVs, for example, when I look for someone who could work in my company, I always ask about the side projects or personal projects, because it also tells me about the person, like is this person really attracted by electronics? Do they do it in their free times? Are they able to solve the problems by themselves? And all these kind of things. If someone just studies and then, okay, I finished this school, now hire me, that's not enough.
Yeah, I agree. Now, there are companies that hire that kind of people specifically because they're not looking for designers, just people who they give tasks to. But there are other companies who are more conscious about making good products, and they are specifically looking for designers. So it's a designer mindset. And one proof of the designer mindset is whether you're only doing it for the money or not. If you did hobby project, you spent your pocket money on it while you were a student, that's a proof that you are interested in it. You have to be interested in electronics in order to be a good design engineer. It cannot be cannot be done with a reduced effort. It has to be with a lot of interest. You really have to figure out why this bug doesn't work, or really have to figure out which is the best chip to do a certain function on your design. Otherwise, the designs will be so bad they will never work, or they will work, but they will not be very good designs. And some companies care about making good designs, and they are looking for the
because
people who care about.
Very often when I design boards, I don't only think about the specification, but very often you have also options like, oh, maybe we can also put there this, and if it works, it is like extra feature for, I don't know, one extra component or something, or I have to keep thinking like, okay, but this is something completely new. If it doesn't work, what are the alternatives? Can we integrate these alternatives into circuit and then just test it if there is problem? Or it's not only focusing on the specification, but you have to think about many other things and different
Curiosity.
views.
curiosity, right?
Yeah.
Okay, that's the last one is that all electrical engineers are designing circuit boards. Actually, it's probably
Oh,
maybe
no, no, you
10%.
skip number 13, and I would like to point out because
Okay.
there are many people who will send me email like, after I watch your course, after I watch your video, can I design motherboard? So
So they have to have the curiosity. They have to read. Well, for the simple board level, probably at least one book, but later, if you want to progress, read more books. Just download KiCad doesn't help because you actually have to use it. I mean, some people just say that I have a book on my bookshelf. I didn't even really open it, but I have it, and now I want a job. So that doesn't really work either.
yeah, it's same for watching videos. Um, I have this platform for online courses, and sometimes
Hmm.
when I talk potential instructors, some of the people are worried, like, but I will share my knowledge, and then everyone will know what I know, and they can do what I do. But I'm like, in 2 hours, you are not going to share all your knowledge what you ever thought. In 2 hours, you can say something what is also important, but that's that's not enough to actually be really good at something. You have to do it for, I don't know,
Yeah,
specific.
learn from projects and
Yes,
learn from the people
exactly.
around you and learn from any document. If you during the design you have to read data sheets, you learn even from those. You recognize patterns. So there's a lot of learning required for hardware design. I think hardware designers have, in order to be a hardware designer, you have to learn a lot more than with most other professions.
Yeah, it's not just like
Um,
watching 1 2 hour video and then you will become expert. That's not how it works.
Even if they watch all the videos, they have to be able to understand it. They have to be curious to pay attention the whole time and they have to think about how this matches with my last project or how this compares to the next thing that I want to do.
This is very good point because and it applies for many different fields, not only electronics. But I remember things like when you watch or when you read something once, and then when you do it and then you read it again, you actually notice the things which you completely missed the first time, and you thought maybe they are not important or you never even see them there.
Yes, that,
So
that's
yeah.
that's true for books, but also true for data sheets. So we might read the same data sheet multiple times, the beginning and the middle and the end of the project.
Yeah, because first time you have some kind of knowledge, and then you use this
And
knowledge on the
assumptions
content
as well.
assumptions, and then as you learn more and more and more, then you will see more and more information in the document.
Yes. Or something that you thought was obvious, then later you find out, oh, actually, I have to pay attention to that.
Exactly.
Okay, and then the last one is, I think maybe about 10% of the electrical engineer graduates will be designing, but there are many of them who end up working in software or firmware development, even though electrical engineering degree, but they still do programming. There are test engineers, manufacturing engineers, um, component engineers, and several other fields, especially at large companies, they have all kinds of these jobs. But even at small to medium companies, it already splits to at least 3 or 4 different fields
Hmm.
from electrical engineering. And that's the ones who deal with circuit boards. There are many electrical engineers who work in the power lines, the power that powers your city, and several other things as
Hmm.
well.
And when we are talking about this again, many questions is coming from people who are asking, uh, do I need to have college to be good hardware design engineer? Like, do I need to
I,
go to
I
university or?
I think they do because as you increase the complexity of your designs, it becomes more of a scientific job rather than a trade-like job. A trade is like an electrician or a plumber or someone who repairs the windows on a house. It's a trade that uh, it's a different kind of mindset. For complex electronics, even for medium complexity, you have to read scientific papers sometimes, and you only understand it if you have a scientific mindset, and that's what the universities really provide. University doesn't really teach you the latest microcontroller or something. Or if they do, that's not the main thing they teach. It's a scientific mindset is what they teach.
For me, at university, what I learned, I think the biggest advantage is the are the basics which you need for very low level of understanding what is actually happening in these circuits. Like they will teach you the math and physics, and the behavior of these fields and all this stuff. Normally you would not probably learn this from like watching YouTube videos or something.
Yes, another thing people learn at universities is how to learn more efficiently.
Exactly.
In the first semester, they just listen to the lecturer. The second or third semester, they figure out that they can learn more efficiently from the textbooks, even though it was written by the lecturer. But still, in my own time, I can go back to different parts and analyze things. That's what they learn. They learn, I think, at universities.
Yeah, and also the basics, as I said, like
Yes, they have to have that.
no, I don't mean like basics of like 1+1, but the basics what you need for understanding what is actually how everything works.
Yes, electromagnetic waves and
Yes,
things like that.
yeah, that's what I mean exactly.
Now, if someone just wants to design a very simple thing with a microcontroller, they might do it without a college degree. I haven't heard anyone doing that. But if any aspirations to doing professional products like things that go into airplanes, data centers, or even a computer, they have to have a scientific mindset from a college degree.
Okay, what is on the next slide?
Tasks. So in basic electronics, you design a schematic and a layout, and then you can pat yourself on the shoulder. I'm done. Good job. But if you design complex hardware, you still design the schematic and the layout, but you do a lot of so-called analysis. I think I have another slide somewhere explaining what analysis is, but there are some screenshots showing different types of analysis. You see, some of them are signal integrity analysis. They produce these curves or eye diagrams. But there are other analysis where, for example, you create diagrams for different subsystems. It's kind of an analysis because you find out what the different subparts have to be in each subsystem. And there are stack-up negotiations. There are calculations of component values. There are RxDX matching in a spreadsheet. Even that's complicated. Sometimes I spend 3 days doing that. Timing analysis, backdrilling analysis,
Pin
port
assignments.
mapping, port assignments, and then pin assignments as well. And there are many others. I think maybe the next slide is about analysis. Yeah, this is it. So diagrams, simulations, and spreadsheets mainly. Maybe I would add one more thing to it is sometimes a text document or a Word document, you write something, even that's an analysis. So there are simulations, pinout, power budget calculations.
This is when we are talking about this. Again, many people ask. So I think there are like two kind of people. What I see around. One of the kind of people, they would like to simulate everything. Like they are going to design a microcontroller board, but before they design it, they would like to simulate it. So I don't know what I can answer on these kinds of questions when they ask, like how you would like to simulate microcontroller board. Do they need to simulate it?
Well, on a microcontroller board, you cannot simulate the microcontroller itself when it's executing software. You can simulate individual traces for signal integrity, or you can simulate a voltage regulator for stability.
But the second kind of people are asking like, what do we need to simulate actually? Or do we need to simulate everything, or, because I usually answer, I don't, I only simulate when I have to break too many rules, or if I'm designing something what
Unusual.
Sorry?
Something unusual.
Exactly, something unusual, yeah.
But you have to know what is usual, what is unusual. That's from experience, and that's why you have to start with a small design and a bigger one and a bigger one and a bigger one. That's why we cannot jump to a big design because we don't know what is usual, what is unusual. And even if you run any of the analysis, you have to know what to expect at the end and compare your expectation against the result. If you just simulate something and here are the diagrams, give it to some other guy and look at it, the whole point of the analysis is that at the end you assess it against your expectations. If you don't have expectations, then and you don't have enough experience for that particular type of complexity. So probably start at a lower complexity first, and once you fully understand everything that was being done and analyzed, and what the analysis results, how they compare to the expectations. Once you fully understand it, then move on to the next complexity level.
So, so to answer the question, we don't have to simulate everything, correct?
No, not everything.
Yeah, because I know some people they would like to simulate everything.
Sometimes we reuse a design, or sometimes we make something that is similar to previous product. So when you're at a company, there's always previous products, either designed by you or by other people. So things that are well understood in previously, you don't have to analyze it again, but you have to understand what's the difference in your design between your design and this previous design. For example, they had a USB, you have a USB, but your USB is longer. So then you have to analyze. But if it's not longer, then maybe it's this kind of the same, so you don't have to analyze it.
Yeah, okay.
So probably I'm not going to read this up, but this was on the screen for a few minutes. So if anyone wants to look into this, they can just read this slide.
I think we mentioned many of these in the slide before.
Oh, yes, we mentioned it already. We already had this slide a few minutes ago. And I just want to point out to some people who expected my book to be about the
Oh, we
first
didn't talk
design.
about your book. So everyone who doesn't know you actually, then you have a
Yes.
book.
So this is my book.
Yeah.
Is the screen mirrored anyway?
No, it's okay. I can see it correctly.
Okay, so my book is about complex digital hardware design. So that's the title, right? It's not simple circuit design. It's not my first design. It's probably my 10th design and onwards. So my book focuses on these more complex designs, and you already have to have experience understanding what a data sheet is, what to expect from it, run some simulations, know what to expect from it before you jump in. Because complexity here goes way up uh, across different types of products, as we discussed earlier.
So, and it basically means that people should always pick the right book for them based on their current knowledge.
Yes, and probably they will have to read several books on the way if they take it all the way. Now there are people who just design microcontroller boards one after another for 20 years. They would not need my book, frankly. For those who work in these complex designs, and many people receive mentorship in a job or trainings. So my book came out last year, and there were complex designs before my book was published. So there were people learning these things in other ways. But my book helps with a little bit more autodidactic learning rather than having to rely on mentors, because not everyone is lucky enough to be surrounded by mentors at a company.
Yeah, I remember I went through your book and I know exactly that the information what is there. I had to learn it the hard way, and I had to put everything together by myself. Like there is information, little bit of information here, little bit of information here and here, and you have to find the connections. So when I went through your book, what I really liked was there is structure, so it's explained, and it's then much easier to understand how everything actually works. Because these complex boards, people have to understand how they work, and that's very important. Otherwise, you can't design them.
Yes, and there's so many aspects to these boards to be working, and all those are explained as well in my book.
Yeah.
So without the mentors, the smarter designers who work at a company where they don't have mentors, with my book, they could take their designs further than without my book. I think it's like it
And faster, I
accelerates
think
it a little,
faster.
accelerates it a little bit. It's
Yeah.
not like that's the only way to learn it, or they learn everyone learns everything from it. It's just it accelerates their learning.
Yeah, I agree.
Testing. So there's testing in electronics. Now, if someone designs basic electronics in a simple product at a small company or a hobby project, they just try to make it work on a bench, and okay, the display displays the hello world. I'm done. It works, right? But in professional electronics, working at a company that sells products, you have to do a lot more testing. And some of this testing can be official, like people have to sign off on they check your test report. You have to write documents about testing. What are you going to test? How are you going to test it? What instruments you're going to use? And then a test results is documented as well. Some companies, it has to be signed off by someone verifying that you actually done it. And other companies, no one signs off. They just want you to do all these tests. And all the actual professional companies, a lot of tests are being done.
Before we talk a little bit more about this, I would like to
Mhm.
mention why this is important, because when I was starting with hardware design, exactly what you just mentioned was happening. I connected everything, it worked, and I was like, it works, and that's it, it's finished. But that's not how it works. If we are going to sell the boards to thousands of people, if these boards are going to work in you know in the in the freezing temperatures or in hot temperatures, it's going to influence the board. When the board is working on your table in your lab, it doesn't mean it's really good design. That's what I learned the hard
Yes.
way.
Every unit has to work all the time, and there's something called a temperature range. So all the electronics products have a temperature range. For consumer electronics, it might be plus 10 degrees to plus 40 degrees or something. For some of the industry, you have to go down to minus 40 degrees to up to like 80 degrees Celsius. And during the testing, you also check it in a thermal chamber at different temperatures, and you have to run the tests. Some of the tests several hours, but there are other tests that are run several times, like a power cycling test. You have to power cycle your unit at different temperatures, like 1,000 times, to ensure that it turns on. But even that only proves that that one unit that you're testing is good. You might want to test several units. And then for high-end industrial electronics, they do the thermal chamber testing for every unit in mass production as well. So they verify that every unit is reliable at all temperatures and will always work.
Yeah, and I would like to point out, many people they may underestimate this, but I've seen so many problems, especially for freezing temperatures, like from memory problems through not oscillating crystals problems, power sequencing problems. All the kind of problems appear in, I don't know, minus 20, minus 40 degrees.
Yes. So first, if you find these problems, we will have to probably alter our design. Uh, some cases software, most of the times is the hardware. And there are design techniques that you have to consider. So the circuit has to be designed to work in this environment. It's not not just a random thing that whether it works or not. If it doesn't work, then sorry. But rather it has to be, for example, if you needed to start up at minus 40 degrees, then probably better not to use crystals, but use these packaged oscillators that are hermetically sealed. There's a little crystal inside and a chip inside the same package. And that is more likely to start up at a cold temperature. But there are several other things, and we are not talking about the technical details here. It's just a learning task. These can be found out in a job or from books.
But I wanted to point out this, that there are really problems in freezing temperatures, and many people they may not realize. And actually, I found this testing in the environmental chamber or thermal chamber super useful to find problems if there is something what is running on the edge. Like it works on your table, but it's just on the edge, for example, with voltages or something. And then when you move the temperature, then you will find out, oh, maybe this power rail is too weak. We need to, I don't know, increase the voltage or something, and then it will work perfectly fine for all the time or something like this. Or
Yes.
repeating some random bugs. For example, sometimes it can be very difficult to repeat some kind of problem or fault. But when we move to thermal chamber or environmental chamber, then we were able to replicate it all the time.
Yes. So in your bench testing, if let's say it crashed once, that's bad enough. But you have to be happy about it that, oh, I found it before it went to the customer. So
Yeah,
then you put it in a chamber, try to reproduce it, make it fail. So if it fails, actually it's not that bad thing, because then you can catch the problem and alter the design before shipping it to the customer. So you have to stress test your design. You have to break it to prove that it's unbreakable. Or if it's breakable, then
you
alter it
need to know
until
where
it
the
becomes
limits are.
unbreakable. Yes. And there has to be design margins as well.
Yeah,
So you have to write several documents. I think I mentioned that some of this test is called DVT, design verification test. So this phrase will come up throughout our career. And there we also have to write a test plan for manufacturing, because in manufacturing every unit is tested before shipping it to the customer. And we have to write down how it's tested. Testing is combined with programming. Complex hardware has a bunch of programmable chips like microcontrollers, EEPROMs, and flash chips. They all have to be programmed during testing. So it's combined together.
yeah. Now we scared many people. Like, oh, I'm not going to be hardware design engineer. It looks too complex. It's not designing microcontrollers,
This is
microcontroller
design
boards.
engineering, actually. Okay, next. What and how? We have to learn about components, how data sheets work, how schematics work, how signal integrity, PCB layout works, how the testing works, all this analysis. We have to learn all that. We have to learn how our design will be manufactured, who will manufacture it, what they need, what we need from them, what they need from us. We have to learn how the hardware interacts with the software. All of these have to be learned. It's not just learning the schematic engineering, how to put a resistor in the schematic. You have to learn all these things as well.
We can talk a little bit about this. For example, I have experience with these components again from my very early days of designing. I remember uh, uh, I I had a task to design something, and I found a chip which was doing exactly what I needed. So I used this chip, and then they sent me 5 samples. I built the product, and then we wanted to order, I don't know, 1,000 pieces, and they didn't have them, or the company disappeared, or the minimum quantity was 10,000. Or then I found out, like, oh, this component stuff, it's kind of complex. And basically what I ended up with is I never used a component which was not available on DigiKey, or I prefer to use like generic components. Ideally, they should have also some kind of replacement parts in different from different manufacturers. So rather than trying to find like very specific chip for specific feature, just I try to make it as generic as possible, because otherwise there can be so many problems.
Yes, so the supply chain is an important consideration in the design, and we have to deal with this a lot. For the main chips in our design, we might talk to the manufacturer of the chip and ask them whether is this chip going to be available until 2035? And let's say we have to know how long a product will be manufactured, because we work at a company that has sales and marketing department, so we have to talk to them as well. So again, when you look at a video about how to enter the schematic, it doesn't say anything about talking to marketing department and what to tell them, what to ask from them. But one of the things is how long we'll be manufacturing it, and we will have to discuss the same with the chip vendor. Is this chip available for this? What's the minimum order quantity? What's the lead time? Some chips, they will they will be able to sell you, just you have to wait 12 months every time you order and as a designer, let's say you find another vendor that is able to ship in 3 months instead of 12 months every time, guaranteed, and then we might think that I should probably use the other vendor, even though the first vendor has a better performance, but we will not be able to ship to our customers or something. Or you would have to stock a lot of components and keep a lot of lock down company cash flow when stocking
Yeah,
components. So all of these have to be considered. So you have to talk to other departments like marketing, manufacturing, and their concerns have to be feedback into the actual design.
exactly. And also what I would like to say, when I see here cross-functional team work, the teamwork is again something what is very very different when I used to work when I compare working by for myself like hobbies and working in a company and also on many projects. So it's not only teamwork with your teammates but also with yourself in future, like all the documentation and explaining stuff and making everything clear, finding related documents or something. It's very different from designing projects for myself.
Yes, and if you work in a team and other people are designing, let's say, the mechanical parts, you have to design your electrical part in a way that the mechanical engineer will not have an impossible job trying to deliver something that cannot exist, but you have to design it in a way that they can work with you. So you have to incorporate other people's concerns into your work as well, constantly, and you have to look for it. Even if they don't tell you, you have to, what about this? Do you think this is going to work? And you have to ask them and be proactive. And
Hmm.
you have to have your work fit in the team, not just expect the team to go and take care of the other things for you.
Yeah, and especially for example, very often may happen someone else will take your project in future because I don't know they will need to design new version of the board or something. Then they need to understand your design. Even you have to if you have to do it by
Yeah.
yourself. It's
So
after
there's
one
some
year you will completely forget about the project.
yeah, there's some documentation to do, and also I try to put comments in my schematic. If something is obvious, then I don't put a comment there, but something I had to think about for 2 days, and I figured it out, and I put one or two sentences there. And this is why it's like that. If
Hmm.
someone reuses it later for another project, oh, what's this? I don't need that, and then they will run
Yeah,
into the same
exactly,
bug as I had.
exactly. So there is a lot of consideration. Mm,
So we have to learn the R&D process and all the people in it. So we learn from schools, books, conferences, we learn from mentors or learn autodidactic ways, probably the combination of these two, but some people rely on one more than the other, depending on the situation. And we learn, the most important learning is the learning
by
in the
doing.
job from the projects. Yes. So we design a product, but we design the manufacturing process of that product. Every product is manufactured slightly differently, and we have to design that process. We have to design the validation. We cannot just get the board and start poking it an oscilloscope. Oh, is it good or bad? We have to plan for it. And we might have to alter our design in a way that it will be testable or it will be manufacturable.
This is again good point when you are talking about manufacturing, because I think every hardware design engineer they should go and see how PCBs are manufactured. They should see how boards are assembled, because or maybe they can at least watch YouTube videos how it is done. But sometimes I see people designing boards the way that they have no idea how it is manufactured, and then they will make it unnecessarily expensive because they use one specific thing which will make it expensive, and they don't have to use it, they don't have to do it that way. They can do it differently and make it much cheaper, but they don't understand how it is manufactured, so they will make this kind of decisions.
Yes, it's called design for manufacturing. Now, the designer has to have experience with manufacturing the previous designs and incorporate it into the current design, but also manufacturing engineers will review the design before it goes out. But I think it mostly relies on the designer's experience with manufacturing. But there are several stages of manufacturing, right? The bare PCB fabrication, then the soldering of the components on it is called assembly, and there is a functional test. There's three stages in manufacturing every electronics product. And as a design engineer, we always go to the last one to be present when they start the first builds. Um, there's an environment with benches and sometimes racks where we test the products functionally. The fabrication, I think I never visited a fabrication facility.
Oh, then you
The
should go, you should go.
the assembly facility I visited a few times, but not for every project. But the test facility I have to visit every project.
Yeah, yeah, okay. I wanted to mention this. So it's not only about drawing schematic.
Yeah.
Okay, what is the next?
There's a list of a few conferences that are
Okay, I
related
like
to.
DesignCon. I like Embedded World. Always go there. I don't know about the others. OCP Summit. I've been there once. Is this the Open Compute Summit?
Yes, that's Facebook's Open
Yeah,
Compute. I think DesignCon is the signal integrity and the
yeah.
high-speed design related stuff. Hot Chips talks about new chips like AI ASICs and new processors. It's not mainly for designers, but designers can attend as well. And then there are others are also similarly um, not geared for designers. Even if we don't attend the conference, probably should get, if we have an opportunity, get the proceedings. The proceedings is all the presentations in a PDF or PowerPoint format, and just read through them because there is a lot of interesting stuff. Not every presentation is useful, so we usually search for the few. Maybe I search for maybe 10% or 20% that interests me, and I read those.
Hmm. I think we can go back. So about conferences, because I often go on different kind of conferences. So exactly as you said, first you need to pick the topics what you are interested in, and sometimes it can be even easier to maybe check the results or the papers at home or the
Hmm.
recorded videos from the conference at home, because uh, very often maybe you know a lot of information from this specific session. You maybe are looking only to learn very specific things, maybe at the end or in the middle. So it can be helpful also to save time sometimes. Just watch it, pre-record it. But if you go to conference in person, then you can meet many like great people. That's I think what I love about conferences the most.
Yeah, sometimes you can walk up to the presenter later, but not when they are presenting, but sometime later
Yeah,
and ask them a question, and
exactly.
many of them are happy to answer. But the questions have to be interesting and some high level, not like, oh, please tell me how to start with engineering. Probably that's not the right way of making connections at a conference.
So do you go to some of these conferences?
While I was living in Silicon Valley, I attended DesignCon several times. I went to Hot Chips once. Maybe EDCon is an online conference. That's the easiest to attend. You don't have to fly there.
Hmm. Okay. Okay, we can go to the next slide.
I mentioned this, whether the work is trade-like or science-like, and I think it becomes more scientific as the complexity increases
Hmm.
and more you work on more professional hardware. People work on a microcontroller board, they might never have to read a scientific paper in their whole life. If they wish to design microcontroller boards until retirement, they just don't. But it doesn't mean that they can say that no one needs to read it, because there are other people who are actually pursuing complex designs and they do need to read it. And when they read it, it's they have to understand it in a scientific way. These are
Hmm.
not like a cookbook, but more like scientific papers with standard structures and standard assertions in them. I think a bachelor's degree is enough in order to understand scientific papers, but you have to train yourself in it. So when someone just graduated, they read their first scientific paper, it might seem weird, but after reading several of them, they will know what to expect from papers. So I think that works for a lot of people. A master's degree helps a little bit, but I think it's not required.
Yeah, because usually you learn all the math and physics in first 2 years.
Yes. This is about signal integrity. As I mentioned, some people think that we don't need signal integrity, and they might be correct for themselves, but they try to expand it and tell everyone, and no one needs signal integrity. I heard someone saying that it was shocking. So as you increase the complexity of your designs, you have to do more and more signal integrity. So people who work in a little bit complex, not very complex designs, they have a certain idea of signal integrity, a few rule of thumb or a few calculations, but even they shouldn't expand it to everyone that signal integrity is 5 rule of thumb and that's it. Actually, maybe for them, for their project, it is, but for other people who work on more complex designs, signal integrity is a lot more involved. You have to deal with a lot more things. Complex rules have to be calculated. like lost budgets or timing analysis. While for the medium complexity, you don't have to calculate that. And if you move even further, then there's a lot of analysis at the high end. I think there are books explaining those. Even my book explains them, but there are complete books about just signal integrity and hundreds of pages. Okay, should we move on?
Yeah. I don't have any questions there. Okay, what do we need to know before our first basic design?
Well, so college degree is required before your first job, but if you do your first design as a student, you don't need to wait until you get a degree.
Yeah, I think I was
You
like
can be
10.
in the process of getting it.
I was like 10 maybe when I designed my first Blinky circuit. I don't know.
I was 13, and so it was middle school, but that was not my goal when I was 13 to just start making products when I'm next year when I'm 14. It was in a process of getting there. So I was supposed to go to university several years later. Okay, read at least one book on basics because at universities it's very scientific. They focus more on mathematics and other stuff. But the latest, especially they don't teach it as a hobby. They teach you to become a corporate employee, which is useful. But if you want to be a designer, probably you need a little more than that. And you can get that from books. Any student can learn schematic and layout. These days, it's so easy. Back in my day, it was a lot harder because they didn't have these really good design software for free on the internet. But now, if you download KiCad, you can design your first microcontroller board, even your first few boards in your learning process. You can design it in KiCad in your own computer. I think everyone can afford to buy a computer these days, get a free software, and then start designing.
I would like to say it's not only about software. Even the PCBs are so cheap
If
that
you order it from China,
yeah,
it's their cheap.
it's and I often use Easy EDA. You don't even need to install the software. You can basically design directly in the browser. So if someone is really interested in electronics, definitely they can do it. There are so many simple projects on internet, and they can even manufacture it, and it can look very professional. You can order not only PCB, you can order also like 3D printed cases, and it will look very, very nice.
And you can order an assembled PCB. I did this once with KiCad. I had to buy the components on DigiKey and then put them in a small bag and send them to China to a company that made it. So I paid maybe a few $100s for the whole thing. They made the bare PCB and then they sold the components on it and they sent me the already assembled board with the SMT components.
Now you don't need to even buy the components separately. You can, for example, when I use Easy EDA, I can immediately see what components they have in stock. So I just use the components they have in stock, and they will manufacture PCB, and immediately it goes to more assembly, and they just put there all the components.
Yes, it's pretty good. I think if people want to be designers, I suggest that they start with hobby when they are students. Don't wait until graduation, but start designing some hobby circuit. They will get a feel to what a circuit is, how it feels like, what can go wrong in it, what kind of problems are there, and what kind of activities, at least for the basic, like you have to order it, oh, a component is missing, or they cannot purchase this resistor, they can purchase that from. So this kind of thinking is what they learn from the first hobby project. It's good to learn it early.
Okay, so what do you suggest? Because one of the very common question is, so how do I start? Like, how do I pick up what kind of project I should design or something?
Well, for hobby projects, it will be something that either you can test at home or you can use at home. It will be something simple. Most people these days start with a microcontroller board. When I started in the 1990s, I haven't heard of microcontrollers then. So it was with transistors, but later I got into microcontrollers.
Same for me.
So they can design something with an 8-bit microcontroller, some one or two connectors, some LEDs. It doesn't even have to be a super useful product. It's not for Not you don't have to market it. You don't have to sell 10,000 units of it. Design something that has a display that puts a number on it to measure the temperature, something that is only useful for the design process. It doesn't have to be useful as a product.
Yeah, I agree. I agree. But they still can design. I think many people design like meteo stations or maybe clock or I recently I designed I don't know USB keyboard. These kind of like things are very small and they may be even useful.
So they also part of the learning is you have to understand that there are programmable components like FPGAs, microcontrollers. So it's good to start with a board design with an 8-bit microcontroller, a 7-segment display, a LED, and a temperature sensor maybe. And then if it doesn't work, they will redesign it. Probably the first design will be full of bugs, so it shouldn't be very complex, and expect that maybe the second or third one will work only. But you have to also work on trying to make it work. Put the effort of trying to make it work. I have to cut traces and solder wires or remove a component, put a different one on it. It will look really ugly for the first one or two designs, but by the time you get a job, you've completed maybe 3 hobby projects and you can do a clean design in your first job. It would be awesome. And some companies are looking for that kind of people who have that.
Yeah. Okay, we can move to the next point.
Um, we can study existing designs. There are reference designs from component companies, processor companies. Some of this is available for free on the internet on their website, but others are not. For example, Intel reference design is not available from an Intel website to run on people, only people with an NDA. But there are others, companies like Microchip making these microcontrollers. They do have reference design that anyone can download. So find the ones that are available and learn from those.
You know,
You can
yeah, go ahead, go ahead.
they provide a schematic and a layout file sometimes, and it just look at how they did it and try to imitate it.
hmm You know what I found very surprising? Like a couple of times I explained people how actually very often boards are designed. Like you take reference boards, you connect them together, and you create your board. And number of times people were like, "What? I thought I have to design everything from like every single resistor and putting everything together." I'm like, no, like ideally, if you are not sure, if you are beginner, and even very often, even when you are designing very complex boards, you just take the pieces which you know they are working, and then you just connect everything together because it's much faster and there is much higher chance that everything is going to work. Or what's your opinion?
Sometimes. So there are different levels to this. One, what you said is just try to copy the whole reference design. Now, if it's in a PDF, you still have to draw the schematic, which is you have 2 screens and look at the reference design and try to make the same thing. But what I like to do is I like to design based on the data sheet, but there you can divide your work down into microscopic details like this pin, this resistor, this signal, that signal. And while I'm designing this signal, drawing it in a schematic, I also look at it in the reference. How did they do it? So first in the data sheet, I decide how I want to do it. Then I look it up in the reference how they did it, just to verify whether my idea about how I want to do it was good or bad. Now, if it's different, then you have to analyze why is it different. Maybe I'm have a better idea, or maybe they had a better idea, but you have to compare it.
Yeah,
But
but
if it's the same,
for someone who is starting with electronics, I think this is too risky because you very often you need to check multiple places, not only there may be multiple reference designs, multiple data sheets, multiple things. Because I know exactly what you are talking about when I design very complex boards. But I think this would be too difficult for beginners.
I think for beginners, they should still check the data sheet and try to decide what they want to do, but copy the reference design. And if what they thought was different than the reference design, they have to study the data sheets
Yeah,
again. Why I thought that I wanted to do it this way, but the
yeah,
reference design did it
yeah,
that
yeah,
way.
yeah.
But with more experience, it will be a little bit smoother. There'll be less research to do, but still there is a comparison between what
Yeah.
I would do and what the reference design is. when the reliance on my own idea versus the reference design idea shifts. The early designs, when they are different, I just go with the reference design. When I'm more experienced, then I compare it and I make a calculated risk to go with
Exactly,
mine.
exactly, exactly. That's what I meant. But I was very surprised that many people thought like you are designing everything from scratch. No, like if you are going to design 200 pages schematic, you are not going to design everything from scratch.
Yes, there are reference designs for the processor, the chipset, the voltage regulators, the clock chips. Everything has a reference design.
Yeah. Okay.
And
Watching YouTube.
YouTube videos as well. But just YouTube videos are not enough to become a design engineer. But I think they help. Just like any book accelerates learning, the same with YouTube videos.
My YouTube videos are good.
Yeah, especially Robert's YouTube videos. There is a very long selection of those. So I wanted to point this out. It's very important. There's top-down learning and bottom-up learning. As we were talking about in the last 30 minutes was probably the bottom-up learning. Yeah, someone starts with a simple design and they start their career with a simple design, do everything on it. Then once it's done, go on, do another design. It's slightly more complex and then more complex and so on. That's bottom-up learning. It increase the complexity of the designs over time. And most of this bottom-up learning is also combined with figuring out what to do and how to do it by myself, reading books, or even if there are mentors, you go to the mentor with a specific question. While they in top-down learning, it is common at large corporations, but some of the smaller companies also do it. They hire fresh graduates who never designed anything, and they give them tasks in other
Mm-hmm.
people's projects. For example, go and analyze this resistor for me, or go check the pricing on that component for me. And then they are given random tasks that take maybe a few days or a few weeks to do, and they are given random tasks for the first few years. And then the company expects them to piece it together into a project. Now, I don't think that they can really piece it together very well, but these companies trust that they can. So they give them a smaller project after several years of doing tasks.
Mm-hmm.
And in their first project, they will have a heavy mentorship assigned to them. There's also a corporate process guiding them what they have to do. And then they increase the design complexity from there. But it's a different kind of mindset. So top down versus bottom up learning.
Mm-hmm.
I did the bottom up learning, and you did that too. I know.
Mm-hmm. Yeah.
But if we start working in especially if we apply for a job after college at a big company, and if we get a job there, then there will be a lot of people around us who are engaging in top down learning.
Mm-hmm. But it's I think what I again what I read a lot is people who are trying to find job in hardware design. Very often they complain that the company is only looking for senior engineers and they are junior engineers or they have no experience. So how they can get a job if no one if they have no opportunity to learn? So
So there are two types of companies, I think, and even with a company, there are two types of managers or departments. Some people are looking for designers who already design things. But there are other companies who are not looking for designers. They are looking for fresh graduates and they only check their grades. And they expect those companies are invested in top-down learning. They expect the company to teach them. So there are companies that will teach you engineering and they will teach you that through top-down learning for giving tasks first before giving designs. There are several companies that hire fresh graduates with no experience. But it might not be. So you have to know when you want to apply for a company, job at a company, you have to know which type they are looking for. You can gauge that from the job description or
mhm,
by talking to a recruiter.
mhm,
But if you want top-down learning, but you want to apply at a company that is invested in bottom-up learning, then they will not hire you, and vice versa as well.
mhm,
So you have to know which company to apply to, depending on how you plan to learn your profession in this top-down or bottom-up approach.
mhm. Okay, we can go to the next one.
A mentorship. Mentorship is when an older engineer, the company will tell you lots of things. Now, you can access mentorship in two ways. Go to the mentor with a specific question. And that's one way. Another one is just, I don't know what this is. Teach me engineering. Even that works in some cases. There are some mentors who will just put a lot of effort into that. They will find you in your cubicle and, hey, could you look at this? Because you will use this in your next assignment. That's mentorship. And then the opposite of mentorship is when you don't have a mentor and you mentor yourself. It's autodidactic learning. You find out what you have to learn and learn it. If you find out about some topic and then start researching it, maybe in Google, some of the search results will be books, others will be forum posts or conference papers, and then you read those and then you try to apply them in your project. Autodidactic learning is more useful for bottom-up learning, while mentorship is more useful for top-down. But in a real life, there is a combination of these with a different percentage for different people.
Hmm. But I found this mentorship quite difficult because there are not like many people who, usually these people who are very experienced, they are super busy, and
Yeah.
also companies they don't want to spend their time teaching younger engineers because they are super expensive. So it's like
Some
very
com
difficult.
some companies do actually, but you have to if you need heavy mentorship, then you have to find a company that provides that. And sometimes people apply for jobs based on company labels or my cousin worked there, I want to work there too. But if your cousin worked differently or learned differently, then maybe you should find a different company that is more suited for your preferred way of learning.
Hmm. Can you find mentor outside of a job, like someone who is like just interested in electronics? Maybe they are at school, university. They would like to have mentor who is going to teach them.
At a school, there might be a hobby electronics club, and you can find out who are in it and then ask them questions. Just walk up to them and ask questions to them, and they become your mentor if they are nice.
But sometimes I remember my experience actually. Once happened to me. We went to a club with friend of mine, the like hobbies electronics club, and the leader, I think he was passionate about electronics, but he was still hobbyist. So it was very
Hmm.
interesting to see, like he was teaching the other people something what I would never teach because I don't think it was always right.
Yes. Now, I think the more talented engineers would rely more on autodidactic learning and rather than mentors. If
Hmm.
someone wants to learn everything from mentors, then it would be a hard career to do. They might be able to make it. They might they might stop needing a mentor after a few years, or they might need a mentor forever, but then probably they will get laid off if that's the case. If they need a mentor several years into their career for everything that they do. So there has to be some autodidactic learning, even if you have a mentor.
Yeah, I
And
agree.
most people never meet a mentor. They never been within a few miles to a mentor, so they just have no choice but try to learn autodidactic ways.
Yeah. I think this is good to point out. So people don't have expectations someone else is going to teach them. They really should know if they have this opportunity, then they are lucky. But
Yeah,
they
it's
should not
luck.
rely on that.
Exactly. Um, Learning options for complex design. So career paths. I think there are three different career paths. The B is what I did and you did is start with hobby design, get a degree, and get a job at a small company that's willing to hire a fresh graduate to design boards right
That's
away,
exactly what happened to me. Yeah.
and to me as well. And then increase the complexity. Now, the small company probably doesn't have very complex designs, so you have to change jobs to another one that already has complex designs, and they hire you as a medium experienced person into their team. So that's what me and Robert did. Another one is very common is uh, people who don't do hobby electronics. They just get a degree, but they apply for internships in their last 1 or 2 years in college. They also have to read books. Then they get a degree and they get a job. The job interview, they will ask you about your internship or what you did there, and based on that, they will either hire you or not. And then they give you tasks for other people's design. So that's actually a top-down learning in this path, and it was bottom-up learning in a B. And then, as I explained this previously, with the top-down learning, so they will be given tasks and bigger tasks, and then small designs and bigger design. Now, there are, I think, people out there who missed hobby electronics, missed internship, didn't do any of that. They got a degree. They were trying to apply for a chief engineer job at Intel, but didn't get it. So they had to take a job as a component sales or as a test engineer, as a programmer. But I think most people will stay in that career pattern. It will be a job. It will be a corporate job. They will have a salary. They can call themselves engineers, and it's a completely normal career. But if they really want to be designers in its later years, some people can make it to transition into a designer career later.
Yeah, I know some of these people, especially from test. Like they start with test,
manufacturing.
they find out they like it, and they would like to move to design.
Now, in order to move into design, in some companies, you just ask the manager, "Hey, can you get me in?" And if they are very lucky, they will get that. But in most cases, they will have to show something that, even though they worked as a test engineer the last 5 years, but they have to still show that they have something to do with designs. And how do they do that? They have to do a hobby project in their own free time, or if they're lucky, a company might provide resources for it, like they buy you a board or something. Do the hobby designs, read books, and then when you ask for the transfer, they might ask you, "Okay, we know you were a manufacturing engineer. We can consider you as a design engineer, but we have to ask you some technical questions, maybe a technical interview. Even if it's an internal transfer, maybe a technical interview, and you will be able to answer those interview questions if you have done these two things: hobby projects on your own money and read some books. You might be able to pass the test. It might be just an informal conversation in a meeting with those managers, or they might even set up an actual job interview for internal transfer. And then they will be given small designs and then bigger designs, or maybe they will be given tasks first and then small designs and bigger designs. But I think the most capable designers come from this B, because of the hobby electronics in the student years. And then, as I said, A is probably the most common at large companies. Hobby electronics. You can do hobby electronics like just put something together. This PCB I made it when I was a student, so I etched it at home, and then just wires all over it, and the wrong size components and things like that. Or you can put some more effort into it, read things, read the data sheets properly, and then design something that is manufactured by an actual company. I did that as well, so when I was a student, but in the later years. Okay, and there's not much here. This is my hobby electrics toolbox. Now, when I was a student, I didn't have this. I had a different one. I had older tools. I didn't have a USB oscilloscope. I had a big oscilloscope with a vacuum tube. It was like really heavy, and I didn't have a microscope. But I had good eyesight back then.
Yeah, I agree. Just the other day I was telling my wife, like, I still remember the times when I was like 25 and I could solder down like 0402 with no problems. And then when I was 30 something, I was like, I can't solder 0402 anymore. Like, what? Without microscope. I mean, without microscope.
Yeah, I think professional engineers always use a microscope for soldering. When we alter our prototypes for debugging, they use a microscope. So someone starting hobby electronics now in 2025, they can buy these tools because they exist and they are cheap enough.
Yeah.
But some of these didn't exist in the 1990s, early 2000s when I needed them.
Yeah, the microscope, for example, microscope is super useful. And only later when I had access to microscope, I find out like how many times you can actually see that your soldering was bad and you have to correct it. Because I spent so much time debugging something and then I found out it's just bad soldering. If you have microscope, you immediately see it's bad soldering.
It's not just that, but you can make a nicer soldering under a microscope than you would otherwise.
Yeah, definitely.
So get a USB oscilloscope, $200-300, solder station with a controllable temperature. I bought this for $40. The multimeter for like $15. And then the microscope is probably the most expensive here, although you can get a cheaper one. Now, this $20 microscope that you see on eBay,
No,
that
don't
with
buy
the
them.
USB, that is not usable for
No,
soldering.
no, no, no.
Either use an optical microscope that's really big and heavy, or use a electronic microscope. This was $300. I think maybe you can get one for like 100, 200, and you have to use it with an HDMI cable connected to the monitor. A USB, if you use a USB, then there's a lag, like 1 second
Exactly,
lag, and you cannot solder with the 1 second lag.
exactly,
HDMI probably less than 100 millisecond lag, and then it's usable. And it
exactly.
has a rig. So for a microscope, when people think of a microscope, they think of this one from the biology class in high school, but it has this bottom metal piece, and it just interferes with your PCB. You need to put the PCB down the bench. You need a microscope that hangs over it, something that doesn't have a base,
Yes.
but something hangs over the decks.
And
So
also,
that's the
you
kind of
need space
microscope.
between the optics and the board.
Yes, and for the solder iron to touch it. So that you have to look for a sort of type of microscope that is like that. And in Amazon, there are many of those. And it comes with a boom stand like this that I attach to the edge of the table, but some of them have just a heavy base that just hang over. And mostly the most important tools are the programming dongles, basically, for your whatever microcontroller you use or FPGA, the chip vendor has the dongle, and just buy that. Manufacturing for hobby and for company projects. For hobby projects, we can make a board at home, but these days, now in 2025, you can get it done in China. If you make a small two-layer board like this big, you can get it for $20, and
Even
including
less, even
shipping.
with shipping, $20 maybe with shipping. I think
Yeah,
the board itself it will be like $1, and
yeah.
you can have it like next week. If you only order PCB, you can have it next week, no problem.
I want to point out making PCBs at home with acids is dangerous and can go into your eyes. And the yield is pretty low. Like I had tried to make a PCB and the traces etch off it, and I have to start over again. And maybe a third or the fourth one I have intact
I've been there.
traces,
I've been
more
there.
or less.
I've been there, and so it means you need to practice a lot to be able to actually make good PCBs at home. But the problem is usually you only can create like one layer PCBs. Two layer are
Yeah,
tricky,
yeah.
and they don't really look good. And there is no mask. There is nothing.
Quality is pretty bad.
Just
So I think
yeah,
right now it's better to order it from China.
yeah, exactly.
Cheaper, and it's just the quality is so much better. And then for hobby project, you solder home, or maybe the Chinese company can solder it for
Yeah,
you.
but soldering at home is definitely cheaper because if you ask someone or if you ask a company to assemble it, then there will be like setup fees and feed fees and I don't know.
Stencil.
Yeah,
Yes, but most of the components are fine pitch, and if you try to solder them at home, you might end up with short. So it's probably better to order that
it depends
manufactured,
how much money you have for the project.
and how many fine pitch components you have as well.
Yeah,
If you have any QFNs, then you can even solder that at home.
you can use hot air soldering station, but you need to have a little bit of practice. So ideally, if someone is
A
like
lot of
beginner, maybe
practice.
don't use this kind of footprints. Use like bigger footprints, easy for hand soldering.
Yeah, yeah, definitely. And then the test is just testing it with your USB oscilloscope. Right, companies, the manufacturing is ordered bare boards from a proper contractor. There's a purchase order, goes to the procurement department, and then assembly is, some companies have a production line, an SMT production line. It's a factory. Others outsource it to a contract manufacturer. And then sometimes you have internal manufacturing engineers who interface with the contract manufacturers every day, and you only interface with them sometimes. And the test in the company has typically a lab with proper oscilloscopes and stuff for prototype, but the production test is done in a factory, and we travel to the factory for the first production units being tested to make sure everything goes right.
Yeah, I have same experience.
Okay, we are almost running out of time and we have 10 slides, so maybe we can do it a little faster. We have to work with software engineers. It's not trivial. For low complexity boards, we don't even need a software engineer. Just write a little code in C, maybe 50 lines, and it just blinks the LEDs or puts something. But for professional projects that are always more complex than an LED blinking, we have to split the hardware and software engineering. We have software engineering departments, full-time software engineers work on these things. High complexity boards, even the software engineering splits into different disciplines. There are BIOS engineers, IPMI management firmware engineers, there are test software engineers, there are production test software engineers, there are software engineers writing drivers in the user application. So we have to work with all of those, and our board has to be designed in a way that it works with all of those software to be running on it, as well as the software engineers to be able to put their software on it, test it in a way that they get feedback from it. It's very complicated. We learned this in a job, how to do that properly.
So does it mean a hardware design engineer, it should also know some software? I know the answer, but we need to talk about this.
In my opinion, the hardware engineer has to know what pieces of work the software engineers deliver. For example, they write the drivers, or in the BIOS, they have to set up the memory training and the PCI scan and this. Just know what modules are in the software. It doesn't mean we have to write the code or we have to compile anything. We just have to know what's in the software.
But if we go to, I don't know, like some of the CPLD or FPGA or this kind of, or
Yes.
small microcontrollers, maybe it can be useful if actually hardware design engineer knows how to write some of the code.
Yes, so for the smaller ones, probably. For larger FPGAs, sometimes there are a complete department with 50 FPGA engineers working on it for years. So we cannot do all that for ourselves, that's why it splits. But for small FPGA, for a glue logic or power sequencing, I write the code myself, and it takes about 1 week to do that, maybe 2 weeks. So I do that. So it is worth understanding how VHDL or variable coding works. Actually, the code writing and compiling and testing it.
Mm-hmm. Okay.
Basically, we have to be able to work together. So we have to know what they are doing. We don't have to reproduce everything that they do, but we just have to know what to talk about.
Yeah.
Working with other disciplines, we have to work with several other disciplines, and the same is true. We have to know what they are doing, and we have to know what we have to do for them to be able to do their jobs. So it's again about teamwork. You have to work with all of these disciplines. In hobby electronics, none of these people exist, but in professional companies, all of them exist. I mean, maybe small companies have maybe half of these disciplines. Large companies have all of them, sometimes even more.
Mm-hmm.
Is it the same?
Oh, what is in working in mass production?
Oh, I skipped that one. I think I mentioned some of these. The production facility has several stages, right? The PCB fabrication, where they make the bare board with the traces on it. There's SMT assembly, and in many product types, there's a mechanical assembly station as well, because some products have, especially the ones that go in a chassis, there are many mechanical parts that have to be assembled together with the boards as well. So metal and PCBs stacked
Cables,
together
yeah.
in very complicated ways. But it's
Heatsink.
a mechanical station, and there's a functional test station that we designers interact with the most, where each unit is tested whether they are working, and then they are programmed as well.
But when we are on this, when I see here Proto 1, Proto 2, so I come up with this topic what we could talk about a little bit. So how is it? Like you design board and it goes immediately to mass production, or because normally, for example, we design and manufacture only 10 boards initially, for example, and then we test them, we do the verifications and everything. Or 5 boards, 10 or 5, depends how much money you have.
Yeah.
But definitely not one board, because very often for very first batch, half of the boards may not work because of the assembly problems, because it's very small batch or something. So what is your experience from this kind of point of view, like how to start with this production?
So the project has to be planned to have a prototype run at the beginning. So everyone has to plan for it. Everyone has to know that we are making prototypes first. Now, my experience is for complex boards, the prototype never works. So there are always some alterations that have to be done. The alterations can be cut traces, solder wires. Ideally, sometimes we don't have to cut any traces. But what happens most of the time or all the time is some resistor values have to be changed, especially around the voltage regulators or some pull-ups or something. Let's say change from 1 kilo ohm to 10 kilo ohm or something like that. That's why we need a microscope and a solder station. So we make these alterations to debugging. So the purpose of the prototype is to debug it, because when we design something, there's bugs in it, and we couldn't eliminate all the bugs. So we eliminate them in a prototype. That's why we have a prototype. So we start testing it in a logical sequence. I wrote about this in my book about what order we have to test out the different things in order to be successful. And as we test it out, we run into circuits on the board that don't work, and then we analyze them. We analyze the data sheets, we do measurements, we run functional tests, we run signal measurements, and we try to investigate why it doesn't work the way expected.
I would like to say, when you say it doesn't work, it doesn't mean everything doesn't work or nothing doesn't work. Very often, most of the board may work perfectly fine, but there will be some small sub-circuits which may not.
Yes. So in a complex board, there might be, let's say, 50 circuits in it, just to simplify it, and maybe 5 of them don't work. But the other 45 does work, but they cannot work because of the other, they rely on these 5. So for a complex board to work, you need, let's say, the console to report that all the tests were successful, but it doesn't report that because some of the circuits don't work. You have to find out which circuits don't work and alter them under a microscope and solder iron to make them work. And then you have an altered prototype. You have to write down all the alterations.
Write down, very important, write down.
Yeah. So once everything works, once the whole board functions and it says test successful on the console, then go back to the schematic editor and implement all the changes from these alterations from the doc list. And then we update the layout as well, because some traces will change sometimes. And that would be the Proto 2. Now the Proto 2 is expected to fully work. And they also make a few units, not that many, maybe 10. And then we test the Proto 2. Now it will be a lot easier to test the Proto 2 than it was to test the Proto 1. So if it fully works, then we just order more as production units and start manufacturing them. If it doesn't work, then we debug it again. It will be a lot shorter debugging. Let's say you might spend a month debugging Proto 1, you spend 3 days debugging Proto 2. And if there are alterations of Proto 2, they are like a resistor value change. I don't think companies employ design engineers, they don't expect Proto 2s to be full of cuts and wires, because frankly they would lay off people who do that. So on Proto 2, the only thing you can do is just alter a few resistors. You can replace with a solder iron, but you can apply that into the bill of materials in the company manufacturing database. So then you
So
can
basically,
still go.
Proto 2 is kind of something which may actually go to mass production.
Yes, and then the design has the Gerber files and other files released, and also the bill of materials in the database. So you can alter the bill of materials easily before making more units. You don't have to respin the board and make more to test them.
So how many boards do you make for Proto 1? From your experience, what do you think, what is like good number?
Depending on the company, and it also depends on how many software engineers have to work on it. If it's something that you need a large software team to work on it, you have to make a bunch of Proto 1s, like 10, 20. But if it's just 1 or 2 software engineers work on it, then usually 5 units for Proto 1.
So you have same experience what I have.
Yes.
Yeah.
Sometimes a Proto 2 has a little bit higher volume. So let's say 10, 20,
Hmm.
30 units, because there's a lot more software development involved in when the Proto 2 comes, they're still developing software, but there are more people working on it. And while at the beginning of Proto 1, there might be just one or two software engineers working with you trying to bring up the board. But
Yeah.
after that, there is a lot of several layers of software and software features all have to be implemented for a new board, and they are working on it at that stage. And they will be doing it. They are testing on the Proto 2 boards in the software lab.
Yeah. Okay, we can move to the next because yeah, you are right. We are going out of
Yeah.
time. Ah,
So
this is interesting. Let's talk a little bit about this because I remember uh, when I used to work in the UK, I asked. We had a really good relationship with Intel, and I was like, I really would like to. I would love to work in Intel. And the guy from Intel, he told me like, I don't think you are suitable for work in Intel. I'm like, what? So I wanted to point out, people who are looking for job in big companies, big or small companies, there are big differences how these companies actually work.
yes, they have to find out how the company works. Ask people who work there, either on LinkedIn, or ask your former classmates or friends whether they work there. Try to gauge what type they have. Now, I prepared some of these slides to define what types exist so you know what to ask from your
Yeah,
cousin about working at that company. So, for example, in one aspect, you can categorize companies as horizontal or vertical structures. In a horizontal structure, a design engineer negotiates with mechanical and other engineers, while in a vertical structure, there is some boss in a project who will give orders to both the electrical and mechanical engineers, and this boss figures out how the electrical and mechanical has to fit together, and that boss tells both of them what to do. In the horizontal team, the electrical and mechanical have to negotiate as partners, figuring out what's best to implement both the electrical and mechanical to fit together as a good product. In another aspect, how development is planned and how it's executed, there are process-driven companies and there are agile companies. These terms might not be very common, but we have to introduce terms to categorize them. So a process-driven company, there are these company standards that explain how to do each task in a project and what tasks you have to do in a project and how to do each of them and who has to sign off on it and so on. While in an agile company, the design engineers figure out how they want to do it and then they do it. And also at an agile company, the same engineer can do the next project differently than they did the previous project because the next project might have different needs or different kind of features that have to be developed differently. While in a process-driven company, everything has to be developed the same way, and it might be a little bit inefficient, but at least it's other business divisions can track how the engineering is executed. So it's more planned, calculated. The finances are very, very clearly calculated.
hmm so I would like to explain what I mentioned or what I meant when a friend of mine told me like maybe you are not suitable for Intel, and you don't have it in this list. But uh, the the biggest difference is I really like to do everything, and basically what he told me like if you go to Intel, you will be assigned specific task and you work on this task, and you may not like it because you will not see the whole process, and you know. And he was right actually. I really loved to work on in this whole process of designing. I would not be like very happy probably designing only small task or specific areas or something.
Yes, now some of us, like you and me, who started designing as hobby, we like to be designers, so we like to own the whole thing. Simply, some of the companies are compatible with it, others are not. Now, they have their reasons why they are one way or the other, and we have our reasons why we are one way or the other. So we just have to find out which companies, which type by talking to people, and then not waste our time trying to apply somewhere where they wouldn't hire us because we have a different background than what they are looking for, and we wouldn't like to work there anyway because they don't want us to do what we wanted to do. So we just focus on the path that is compatible with us, and
Yeah,
that would be a much easier life for
yeah.
everyone. This is another important thing. Some companies have one hardware engineer assigned to one board design. Actually, all the companies I worked at were like this.
Hmm. Same for
But
me.
there are some companies where multiple engineers are assigned to one board design, and it can be as much as 100 people with 3 layers of management designing one laptop motherboard, for example. And it's just a different kind of work environment. The same applies as the previous slide. We have to know which type of company is and only apply to the ones that there are many engineers who don't want to own a whole design. They just want to focus on one thing and
Power
just work it
supplies, for
out very well.
example. Yeah.
Yeah, they just want to work it out perfectly. It's just a perfectly fine career path, but some people are different. Some people want this to go this way, other people want to go that way. They just need to know which companies provide that kind of career path.
And I would like to point out, even for this like one guy, one board, uh, we still could get help with from other engineers. Like it doesn't mean I had to design everything by myself. There could be people who help me with, I don't know, power supply design because deadline was in 1 month and I wouldn't have time to do everything by myself. So it doesn't mean I would do completely everything, but I was the one who was responsible for like
Yeah,
finishing it properly.
some people call it a responsible engineer or a product owner. Okay, there's not much left. This was really discussed in the previous slides. Like most small companies support bottom-up learning. Most large companies support top-down learning, but not always and not all of them. It's just like a tendency. It doesn't. So you can find companies that are contradicting this.
Hmm. Well, don't go to next one. So when you are comparing small and big or medium companies, I would recommend everyone try to work also in small company, even if it may not like look attractive because maybe they can't pay so much money or something. I learned so much because in small company I learned whole process of designing boards, and it's very important. It helped me a lot to understand the things which are related to board design, but they are outside of the board design environment. But when I worked in medium company, I was only responsible for, I don't know, designing board, and then I was not really connected much with the other things around the product development.
Yes, if you are in Silicon Valley, then they call a small company a startup, but they just refer to it as a startup. But back in other parts of the country or in Europe, they didn't call it a startup because they might have been around for 30 years, but they're still small. But it's true that the small company you can be responsible for more of the product development, or even if you work with other people, you're more involved with what they do. The large companies, there might be another division in another state or another country that does something, and it's so separated.
Yeah, in small company we even like design the box for the product, like
Yeah, sometimes even the software.
including software.
Okay, so the corporate process, I think, so large companies have a lot of corporate process. Small companies have a small amount, but they can also vary at the same size. Some of the small companies have more than others. And so the process is basically there are the tasks that you do in a project. They would define what tasks you have to do in a project, and they define how those have to be done. And they write these company documents to describe all that, the company standards. There are also international standards for this kind of thing. They're not very commonly used, but some companies do. Some of them have a standard document that describes how to do it. Others just have a tribal knowledge that everyone writes the test back in a certain way, and you just have to see what the other guys were doing and just try to imitate that. Even that is a corporate process.
Again, stop here, because this was big difference when I was working in small company and middle-sized company. Uh, I never realized how these processes can be sometimes very, very useful. So in small company, there were no processes. So we just did whatever we wanted. But then all the kind of problems can be connected with this. Like if there was ECO, like engineering change order. So we had to change something in a prototype or in the board which was in production. Then in the bigger company, there has to be process which has to follow, because everyone who is involved in this project, they need to be informed, they need to know what kind of changes they need to do, because it's not only one person. Like there are test engineers, there is production, there are people who are buying the components or something. So these processes actually can be very useful, but sometimes it was like, I only need to change this resistor and I have to fill out all these papers. Like, what?
Yeah, so the thing about the process, they don't just explain how you have to do something, but they also say that you have to write down what you did
Yes,
in a certain place, in a certain way.
exactly.
So it comes with documentation.
Yeah,
And in one of the previous slides, I had the categories of process-driven company and agile company. So the process-driven company has a lot of this. The agile company have tried to eliminate them or have a very small amount of them.
yeah,
And I think this is the last slide. This is like a generic view of what is done in a product development. Now, each company can add or remove boxes to it, but the most common ones are listed here. For example, design a schematic, a PCB, then get it manufactured and test the prototype, change the design, go to production. And there are analysis tasks, there are DVT tests, there are constraints that to be calculated for the layout and things like that. And this is for, you see there are light blue and dark blue boxes.
yeah.
If someone is doing a hobby project or working at a really small company, they only do the light blue boxes. But bigger companies, they do both the light and the dark blue boxes.
And when I was starting with hardware design, then for me, hardware design was only the schematic box.
Yeah. Well, in
Okay, I did also
manufacturing,
PCB, but like schematic was the most important one. That's what
that's
made the
where the
product.
functionality is, especially for a simple design. There's not a lot of signal integrity in it, so most of it depends on the schematic. But for high-speed designs, we get involved in the layout a lot for signal integrity
Yeah,
purposes. Okay, and that's it.
yeah, that's it. So again, a lot of things what we were talking about, you mentioned also or basically why we are creating this video is to help people to understand who is the right person to read your book, correct?
That as well as also they have to understand what to expect, because it's not good to go through a career and keep getting surprised. Oh, what is that? I never heard of a manufacturing test plan. What is that? So should try to point out in this presentation about what things come up in a job and in a career. And then each of those have to be learned either from books or from colleagues or from doing it.
Yeah, I agree. And then if someone is interested, we also have online courses. But that's not
Yes.
why I'm creating these videos. I do these videos because uh, when I was starting with hardware design, I would love to have all the kind of these of materials what I'm recording with different people, because I could learn so much, and I didn't have to learn on my own mistakes.
Yes, and those who those who already done some simple designs, want to get the complex design, please buy my book, and that would help with those.
Yeah, definitely. Uh, okay. I think I still had some questions, but I completely forgot them, and it's already time to, I don't want to go over 2 hours. So thank you very much, Istvan. If anyone has any questions, what we are talking about, they can leave comments, okay? And also maybe it would be great if people leave comments about their own experience, how they learn hardware design, what they think could help people who are interested in becoming hardware design engineers. So leave comments, and I think it will help many people. So thank you very much, Istvan.
Yeah, thanks for the opportunity.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our FedEval online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments and see you next time. Bye.